This video will examine hypothesis testing for the mean when we have small samples. Since we're dealing with small samples, we should know by now that that means we're going to be dealing with the t-distribution, which again is a family of curves that can be adjusted by degrees of freedom. And that degrees of freedom will be dictated by the size of our sample. So finding critical values on a t-distribution begins, as it does with the z-distribution, of identifying a level of significance, but it varies in identifying the degree of freedom, which will influence the values that we discover. And once we get over 30, it starts to look normal, which is the z-distribution. So we find the critical values using our t-table, and we use n-1 degrees of freedom. If the hypothesis test is left-tailed, we use the one-tail alpha column with a negative sign. If it's right-tailed, it's a one-tail alpha column with a positive sign. If it's two-tailed, we use the two-tail alpha column with negative and positive sign. So if we want to find the critical value for a right-tailed test with alpha at 0.01 and a sample size of 24, the degrees of freedom will be 23. It's 24 minus 1. So we find the critical value with our t-distribution table at 23 degrees of freedom and 0.01 in the one-tail alpha column, because the test is a right-tailed test, and the critical value is therefore going to be positive. If we want to examine the critical values for t in a two-tailed test, and an alpha equals 0.10 level and a sample of n equals 12, then our degrees of freedom will be 11, and we'll use our t-table to look up 11 degrees of freedom at the two-tail alpha column of 0.10, and that will give us the minus and positive t values of 1.796. So the t-test for the mean is a statistical test about the population mean. It can be used when we have a normally distributed population or close to normal. We do not need to know the standard deviation, and n, the sample size, can be small, it can be under 30. So the test statistic is the sample mean. How that got over there. X bar. And the standardized test statistic is t. And to calculate t, we subtract the population mu from our sample average, x bar. And that's divided by the sample standard deviation over the square root of our sample size, n. And the degrees of freedom are always n-1 in this case. So t-test for a mean mu with a small sample and an unknown population standard deviation has these characteristics and words in these steps. We state the claim mathematically, our null and our alternative hypothesis. We identify a level of significance. We determine the degrees of freedom. We then determine critical values using our t-distribution and use that to determine our rejection regions. Next, we find the standardized test statistic. Using this equation, we make a decision to reject or fail to reject the null, and then we interpret that decision in the context of the original claim. So for testing the population mean using critical values, we have an example here of a local telephone company that claims the average length of a phone call is 8 minutes. If we have a random sample of 18 phone calls, which is a small sample under 30, with a sample mean of 7.8 and a standard deviation of 0.5 minutes, we need to know if there's enough evidence here to support the claim of at the alpha equals 0.05 level. So the null is that mu equals 8. The alternative is that does not equal 8. And we have our significance level here of 0.05. Test is two-tailed because it doesn't have a direction. It's just not equal. And degrees of freedom is going to be our sample minus 1, so 17. Critical values are based on that information. We get to negative 2.11 as a negative and positive 2.110 on the right side. So based on that information, we can calculate our test statistic by subtracting the population mean from the sample mean, dividing that by the sample standard deviation over the square root of the sample size the sample size. And we get from that negative 1.7, and that falls within the non-rejection region. We fail to reject the null hypothesis. Here's another example again of the battery manufacturer. We have a random sample of 10 batteries, a mean life of 1,002 charges, and a standard deviation of 14. The claim was that the batteries have an average life greater than 1,000 charges. Do we have the evidence we need to support the claim at the alpha 0.01 level? So the null is that mu is less than or equal to 1,000. The alternative, which is the claim, is that mu is greater than 1,000. And we're at the 0.01 level for alpha. The degree of freedom will be the sample minus 1. That gives us 9. It's very small. And the standardized test statistic can be calculated using that information. And that comes down to 0.45. So if we use 9 degrees of freedom and we go to our TE table, we can determine that P is greater than alpha equals 0.25 over here. So this value of 0.45 falls this way from that, and therefore it is not in the rejection zone. We fail to reject the null hypothesis.